Yeah. So yeah, it's recording now. So you can continue this, or whenever you want, you can record or unrecord.
Sorry, this timing is no constraint, na sir?
No, no constraint at all.
Right, sir.
No
Right, right.
constraint at all. So I'm signing off. I'll be on mute, maybe logged in only. If you have any difficulty, please call me on phone, sir. Any issues?
Right, sir. Right, sir. Right,
Okay.
sir.
Yeah.
Thank you, sir. Hello. Hello, Vishalakshi madam, can you hear me?
Hello.
Hello. Hi,
Hello, sir.
madam. Can
Good
you
afternoon,
listen?
sir.
Good afternoon. Can you listen to me?
Yeah, sir. How are you, sir?
Fine, I'm fine. I think every student is invited for this session.
Yeah, sir. All students, sir. All students will join.
So just now I checked with the whiteboard. Can you see the contents on the board?
Yeah, sir.
Are you using mobile or laptop?
Laptop, sir.
So you need to find out whether it's visible on the mobile phone.
Okay, sir.
Right. We'll check with the students whether they're able to listen. So students, if they want to ask any question, they can use the chat option and they can
Okay, sir.
answer. Yeah. And if they want to ask any question, they can raise their hand
Okay, sir.
that I can answer the question. So uh,
Sir, we will tell to them. We will tell to them that at the end of the class, they may ask the question, sir. Not in between the class.
all the hands raised will address them after the end of the session.
Okay, sir. I'll inform to them, sir.
I'm typing on the chat box, and I think students have started responding also. Uh, they have they have sent that they are able to hear me. Okay.
Uh,
Right. So I'll be using PowerPoints to explain process synchronization today. We'll start with process synchronization today.
okay, sir.
So in between where explanation is required, I'll be using the whiteboard. So please let me know whether you're able to see the whiteboard or not.
Okay, sir.
For the third section, have you started this process synchronization, madam?
Sir, for?
For C section, have you started process synchronization?
No, sir. No, sir. Deadlock only I have finished. It is also this request and that algorithm is request reply algorithm. I have to explain that one also, sir. And this is completed, sir. Last one, inter-process communication is there, no, sir, in the third unit, last part.
Inter-process communication you have finished.
Yeah, sir, I have finished it. Because lab exercise programs are there, sir. That is why I have finished those topics first, sir.
Okay. I'll be
And I,
talking about that only today.
sir, process synchronization, sir.
Yeah, yeah, yeah. So I'll be using different textbooks. I'll not be sticking to Galvin. Uh,
Okay,
you
sir.
just see that you know what algorithms I'm using here and whether they are
I'll
better.
make a note of it. I asked students to write down points, sir, in your PPTs and lecture.
If they want, they can record also. I think the record option is available with them or not. Just let them try. If they, otherwise, I'll record and send the video to them.
Okay, sir.
So I think everybody got clearly what is critical section, what is mutual exclusion, and what is race condition. So I'll just summarize once again. In race condition, what we have seen, two processes are sharing a common resource. Process A and process B were sharing the variable in, and process A and process B were sharing the spool directory. What we have seen there was an uncertainty that when process A was trying to write something in the spool directory, it was preempted in between, and the CPU was given to process B. That led to an inconsistency where the file of process A was able to get printed, but the file of process B will never get printed. That's called the race condition. Then we have seen what is critical section. Critical section means it is the area of the program which is related to sharing of the resource. So if a process has got a set of code in it, which when executed will start using the shared file or shared memory, it's called critical section. That part of the process B which is not related with using of the shared resource, or that part of the process A which is not related to using of the shared file, is called the non-critical section. So critical section is nothing but a block of code which when executed will be using the shared resource. Mutual exclusion means when two processes are sharing a common file, the situation should be that when one is using the file, the other should be excluded from using it. So these are the three important terms which we'll be using in future also. Now let us come back to critical section. See, if process A and process B are using a common file or memory area, we are saying that when process A is using it, process B should not be allowed to use this. By doing this, the file will be consistent, means file will not have any error. But this is not so simple that you just allow only one process to use the file and the other process should not be allowed, and we got a solution for mutual exclusion. No, this is not the solution. To get a good solution, there are 4 conditions that should be met. So whenever you are designing or implementing mutual exclusion, or an operating system is implementing mutual exclusion, if an operating system is designed in such a way that when one process is using a shared resource, the other process should be blocked, or only one process at a time should be using the shared resource, the operating system should take care to see that there are 4 conditions that should be met. Let us see what are those 4 conditions. If these 4 conditions are satisfied, then only you will have a good solution for mutual exclusion. Let us see what is that. So Mahesh Kumar, Sura Mahesh Kumar is asking for explain once. I don't know which topic he wants me to explain once. Mahesh, I will be coming back to you after this class is over. So let us go to the next topic. This is what I wanted to explain you. So these are the 4 conditions which should be kept in mind to design a good solution for mutual exclusion. That is, if you want 2 processes to share a common resource in such a way that when one is using the resource, the other should be prevented, then these 4 conditions should be kept in mind. First one, no 2 processes may be simultaneously inside their critical region. We should not allow 2 processes to enter the critical region at the same time. This is the first condition. This is already we have discussed it. Sorry. So 2 processes should not enter the critical section at the same time. First condition. Second, when you are designing the solution for mutual exclusion, you should also see that there should not be any assumptions made about the speed of the CPU or number of CPUs. See, your design should be such that mutual exclusion should be implemented in any kind of PC with any speed of the CPU. Your CPU is 2.3 gigahertz or 4.0 gigahertz, whatever it might be, your solution should be able to execute in that speed of the CPU also without any problem. Your design should be such that you should be executing in one CPU or multiple CPUs without any problem. So first condition is that two processes should not enter the critical section at the same time. Second condition is that when you are designing the algorithm, you should not have any assumption that my algorithm will work only for one particular CPU or two particular CPU, or my algorithm will work only for this speed of the CPU or that speed of the CPU. Your algorithm should be universal. It should execute on any number of CPUs. It should execute on any CPU or whatever might be the speed of the CPU. Third condition is that if one process is outside the critical section, it should not block the other process to enter the critical section. So for example, if you see here, one moment. What's happening? So first condition says that process A and process B are two cooperating processes. So both these processes should not enter the critical section at the same time. When one is in the critical section, the other should be stopped. This is the first condition. Second condition says that when, I'll erase this. Second condition says that when process B or process A are executing in the non-critical section, so process B, let us say, is executing in the non-critical section, it should not stop process A to enter the critical section. I think in the beginning you will not be able to understand how it will happen, but I'll take an example and show you that. What the second condition says is that you should not assume the speed of the CPU. You should not assume the number of CPUs when you are designing the algorithm. What third condition says that when one particular process is executing in the non-critical section, it should not prevent the other process to enter the critical section. So that is what is the meaning of third condition. Next, what the fourth condition has to say. The fourth condition says that no process should wait forever to enter its critical section. Means you should not design an algorithm in such a way that when one process is in the critical section, the other process should not wait for indefinite amount of time. So no process should wait forever to enter its critical section. Means when process B is in the critical section, process A should not be allowed to enter the critical section. But the waiting time of process A should be expected, definite. It should not be indefinite. So at certain times, what happens is you are designing an algorithm very poorly. So when one process A is in the critical section, you are keeping process B waiting for indefinite of time to access the same resource. So if process A is sharing a file with process B, when process A is sharing the file, when process A is using the file, you are keeping the process B waiting for some time. The time should be definite. If the time is indefinite, then your algorithm is failed. Your design has failed. So when you are designing an algorithm or a program in such a manner that you want to implement mutual exclusion or a good solution of mutual exclusion, then all these four conditions should be satisfied. If one of the condition doesn't satisfy, then your solution is not a good solution. That's the meaning of it. So all the four conditions should be satisfied. Let us take one example and we'll find out whether that example or that algorithm will satisfy all these four conditions. See, this diagram is very clear. I think you can understand in a better way. Now what is happening here, just see. This is process A, this is process B. At time T1, process A has entered the critical section. So this is denoting the critical section. So at time T1, process A starts executing in the critical section. Or process A starts executing that code which will use the file. When process A is executing the code which is using the shared resource for some time, that's from T1 to T2, at T2, process B also wants to use the same file. But what's happening? Process B, when it's attempting to enter the critical section, process B gets blocked. How long process B will be blocked? Till process A completes execution. So process A will complete execution at time T3. As soon as process A completes its execution at time T3, then the file will be free or the shared memory will be free and B enters the critical section. A leaves the critical region. As soon as A leaves the critical region, process B enters the critical region. So when process B enters the critical region, process A is performing some other operations. Maybe it's in the non-critical section. So process B will use the shared memory or the shared file from time T3 to T4. After T4, process B will leave the critical region. So process B has finished with the critical section. It will then enter into the non-critical section. So what you're saying here is that when process A is in its critical region, process B is blocked. When process B is in the critical region, process A is not in the critical region, it's performing some non-critical section. So this is an example. This diagram shows how mutual exclusion can be implemented. That is, only one process at a time will be able to use the resource. I hope all of you are understanding. So let me now go directly to an example, and there we'll see whether this algorithm satisfies all the conditions or not. So please remember four conditions. One is no two processes should not enter the critical section at the same time. Second condition is that you should not assume the speed of the CPU or the number of CPUs. Third condition is that a process which is in the critical section should not block a process which is in the non-critical section. Like say here, process A is in the non-critical section and it should not block the other process to enter the critical section. And fourth condition is that this process B, which is blocked when process A is in the critical region, the blocking period should not be indefinite, it should be definite. Let us take one example of critical section problem. So what's critical section problem? Critical section problem is where we should allow only one process to enter the critical section at one time. Two processes should not be allowed to enter the critical section at the same time. So let us see here. Process X and process Y. Now, before that, I want to know why will a process get preempted? Why will a process get preempted? See, process will get preempted because of interrupts. Particularly clock interrupt. Sorry. What is clock interrupt? Now let us say, for example, process X starts executing. It will be allotted some time slice. If this time slice is over, the clock will be interrupted. The timer will stop and the CPU will preempt process A and the CPU will be given to process Y. So basically the preemption of process is occurring because of interrupts. Now let us see one solution for a critical section problem, where when process X is using the critical section, process Y should be stopped. So how will we do that? Let us say this example. We want that when process X is in the critical section, it should not be removed from the CPU. So how will it happen? It will happen only when we disable the interrupts. So when interrupts are disabled, when the CPU will not receive any clock interrupt or timer interrupt, process X will not be removed from the CPU. So using this concept, what we'll do is we design an algorithm for a critical section problem. One is process X, another is process Y. So process X, what it does is before entering the critical section, it will disable all the interrupts and it will start executing the critical section. Since this interrupts and clock is disabled, there is no question of the CPU preempting process X. So process X will be not disturbed till it completes the critical section. But after completing the critical section, process X has to enable the interrupts. So once the interrupts are enabled by process X, it will then enter into the critical section, and then process Y can plan to enter the critical section. So when process Y also wants to enter the critical section, it will disable the interrupts first and then starts executing the code in the critical section. As long as process Y is in the critical section, it will not get disturbed because the clock interrupts are disabled. So even if process X wants to enter the critical section here, it cannot because interrupts are disabled. Process Y will not be preempted. Process X can execute only when process Y is preempted. But the situation here is that process Y has disabled all the interrupts. So there is no question of process Y getting interrupted. And since process Y never gets interrupted, it will execute the critical section without any disturbance. And as long as process Y is executing in the critical section, no other process can send the interrupt to the CPU, and the CPU cannot preempt even process Y also. So process Y will execute its critical section, then it will enable the interrupts after coming out of the critical section. Once process Y enables the interrupts, process X can enter the critical section at any point of time. So you see this program here. What do you see here is that there are two processes, process X, process Y. Before process Y enters the critical section, it will so before process Y enters the critical section, it will first disable the interrupts or the clock interrupts, enters into the critical section. When process X is in the critical section, process Y will be outside. It cannot enter. After process X completes the execution of critical section code, it will then enable the interrupts that will allow the CPU to preempt process X. And if CPU preempts process X, process Y can be given the CPU, and again CPU, when it's given to process Y can enter the critical section. So the question is whether we should allow a process or user process. Can a user process be allowed to disable and enable the interrupts? See, generally the interrupts are enabled and disabled by only the operating systems. If we give this privilege to process X and process Y, which are user processes, what may happen is that process X may disable the interrupts, and if something goes wrong in the critical section and process X is blocked or gets terminated in between, it will not be able to enable the interrupts. If it is not able to enable the interrupts, then the entire system will be blocked. So we should not give the privilege of enabling or disabling the interrupts to user process, which should be only with the operating systems. So that is what this solution cannot be a perfect solution, because a process may disable the interrupt, okay, fine. But if it is unable to enable the interrupts, the system gets blocked. No other process can execute, the system will be blocked. So this is not a good solution for mutual exclusion, implementing mutual exclusion. Another thing is that this is only for one single CPU. If suppose the system has got dual core or quad core, means there are more than one CPU in the system. And if you disable the interrupt will be disabled only for one CPU, but the other CPUs will be executing. So what happens here? Process X may disable the interrupt for one CPU, but process Y can execute in another CPU. It can execute in CPU 2 or CPU 3 or CPU 4. So mutual exclusion will not be implemented in that case. What will happen? Process X is executing in CPU 1. So process X is executing in CPU 1. It has disabled the interrupts for CPU 1. But there is CPU 2. So what will happen? Process Y will execute in CPU 2. When process Y is executing in CPU 2, it will access the same file which is used by PX. So both will enter the critical section at the same time. So this solution will not work for multiple CPUs. It will work only for a single CPU. And there also you have to be very careful, because we cannot give the authority to user process to disable the interrupts or enable the interrupts. So this is not a good solution actually. Now next we'll move to the next solution. So students, are you able to understand? If you're able to understand, please raise your hands. Are you understanding? Sure. Okay, so most of them have raised the hand. Right. Now let us go to the next algorithm. See, this is a very simple algorithm. It it is a software solution to mutual exclusion. It's called lock variables. Now what happens here, just see. There are two processes again, process X and process Y. So process X and process Y are sharing the same file. Initially, if both wants to, if any of the process wants to enter the critical section, what they have to see is they have to first find that whether the file that is shared by these two processes, say this is the file, this file X is shared by process X and process Y. Now, if process X wants to use this file X or process Y wants to use this file X, first they have to find whether this file X is free. How to find that? For that, we are using a flag or a lock variable. If the value of this lock is 0, it means file is free. If the value of lock is equal to 0, file is free. If the value of lock is equal to 1, file is busy. So if process X wants to use this file, it has to check whether the value of lock is 0 or 1. Now, one more thing. Please understand this. I'll use the whiteboard. Clear this. If suppose we have a statement in a program called while and the condition is true and it is terminated by a semicolon, what happens is that as long as this condition is true, the CPU will go on checking the condition again and again. See, let us say lock is a variable, Boolean variable. Lock is Boolean variable. Boolean means it can have either a 0 or 1 value. So if I say while lock and the sentence is terminated, and suppose the while is terminated by a semicolon, if the value of lock is equal to 0, 0 means false. So while false means this statement will not be executed, the control will come to the next line. If lock is 0, if it is false. If this condition is false, while loop will not be executed, the control will come to the next line. But suppose this condition is true. Say lock is equal to 1, means condition is true, lock is 1. So when the condition is true in a while statement, which is terminated by a semicolon, this loop will go on executing again and again till the condition becomes false. So as long as the condition in the while loop is true, that is terminated by a semicolon, the CPU will go on testing the while loop, or the CPU will go on executing the while loop till this condition becomes false. So this kind of situation where the while loop is continuously executed till the condition goes false is called busy waiting. This is called busy waiting. Now what happens in the, let us go back to the algorithm. So in this algorithm, the notations. Okay. In this algorithm, if lock is equal to 0, file is free. If lock is equal to 1, file is in use. So let us say initially value of lock is 0. Process X wants to execute. What process X will do? It will check the value of while lock here. Lock is what? 0. So while 0 means false. So while loop will not be executed, the control comes to the next line. So what process X will do? It will set the value of lock to 1. Lock is equal to 1 means file is in use by process X. So after setting the value of lock to 1, process X will enter the critical section. When process X is in the critical section, at that time, let us say process Y wants to enter the critical section. So what process Y will do? It will check the value of lock. Lock is 1. Lock is 1 means condition is true. Condition is true means the while loop will be executed continuously. The CPU will go on executing the while loop again and again till this condition becomes false. That means what? When process X is in the critical section, here process Y is outside the critical section. This is the critical section of process Y. So when process X is in the critical section, process Y is outside its critical section, means it's only testing the value of lock, it cannot enter the critical section. So when process X is in the critical section, process Y cannot enter the critical section. After process X completes the critical section, it will set the value of lock to 0. So lock becomes 0. When lock becomes 0, this condition becomes false. When this condition becomes false, process Y will set the value of lock to 1 and process Y now will enter the critical section. So when process Y is in the critical section, at that time process X is in the non-critical section. So perfectly we are able to implement the condition that only one process should enter the critical section at a time by using this simple concept of lock variables. But this solution, as you look, is not 100%, or it's not a perfect solution. We'll see what exactly happens wrong here. Say process X starts first. Lock is 0. That means file is free. So process X will start first. It will check the value of lock. Lock is 0. That means condition is false. Condition is false means file is free. But what happens is before it can set the value of lock to 1, it gets preempted here. It gets preempted here. The time slice of process X is over. So CPU will preempt the process X before it sets the value of lock equals to 1. CPU is given to process Y. Now what process Y will do is, it will also check the value of lock. Lock is 0. So condition is false. Process Y will set the value of lock to 1 and enters the critical section. So after process Y enters into the critical section, let us say the time slice of process Y is over. So process Y is preempted. When process Y is preempted here, CPU is given to process X again. Process X was preempted here. Means it has executed already lock. It has already just tested the value of lock, which was false. So it will not execute the same statement once again. So what it does is, since it was preempted after checking the value of lock, which was false at that time, when the CPU is given back to process X, it will start executing the next line, that is setting the value of lock to 1. Lock was already 1, it will again set the value of lock to 1, and process X also enters the critical section. So both the processes are in the critical section at the same time. This algorithm fails. So what is the first condition of the good solution for mutual exclusion? Two processes should not be into the critical section at the same time. So what's happening in this algorithm? The first condition itself is not satisfied. So this algorithm is not a good solution for mutual exclusion. Right. So this solution has failed to satisfy the first condition itself. Let us see the next algorithm. This algorithm is called strict alternation algorithm. This algorithm is called strict alternation algorithm. Let us see what happens here. There is a variable called turn here. There is a variable called turn. Why this variable is used? If the value of variable turn is equal to 0, then P0 can enter critical section. But if the value of turn is equal to 1, then P1 can enter the critical section. So this is an algorithm where there are two processes, P0 and P1. They are sharing a common resource or a file or a memory area. Condition is that when turn is equal to 1, process 1 can enter the critical section. When turn is equal to 0, process 0 can enter the critical section. So when process 0 is in critical section, the value of turn will be equal to 0. When process 1 wants to enter the critical section, at that time the value of turn is equal to 1. So when turn is equal to 1, process 0 cannot enter the critical section. When turn is equal to 0, process 1 cannot enter the critical section. That's why it's called strict alternation algorithm, which means that when one process is in the critical section, the other should not be in the critical section. Let us understand this algorithm. Initially, let us say the value of turn is equal to turn is initially equal to 0. Process 0 wants to enter the critical section. So what process 0 will do? It will check whether turn is equal to 0. Yes, turn is equal to 0. So turn not equal to 0 will be false. Since turn is equal to 0, the condition turn not equal to 0 will be false. So process 0 enters the critical section. So when process 0 is in the critical section, at that time, if process 1 wants to enter the critical section, it will check the condition turn not equal to 1. What is the value of turn? 0. So 0 not equal to 1 will be true. So process 1 cannot enter the critical section. It will go on checking the value of turn again and again as long as process 0 is in the critical section. After process 0 completes the critical section execution, it will then set the value of turn equals to 1. So the moment the value of turn becomes 1, process 1, what it was doing, it was going on testing the value of turn again and again. So turn was 0 earlier, that's why it was in busy waiting. Now turn becomes 1. So 1 not equal to 1 will be false. So while loop will not be executed, process 1 enters into the critical section. So when process 1 is in the critical section, at that time process 0 is in the non-critical section. Again, we see that when process 0 was in the critical section, process 1 was testing the value of turn, it was outside the critical section. When process 1 is in the critical section at the time process 0 is in the non-critical section. So what we see here is that process 1 is in the critical section, process 0 is in the non-critical section. Similarly, when process 0 is in the critical section, process 1 will be in the non-critical section. The solution looks to be successful, but it's not. Let us see how. Initially, turn is equal to 0. Process P0 checks the condition here. Turn is 0. So 0 not equal to 0 is false. Process 0 enters the critical section, executes the critical section, sets the value of turn equals to 1, enters into the non-critical section. So process 0 is in the non-critical section. Process 1 wants to enter the critical section. So it will check the value of turn. Turn is 1. So 1 not equal to 1 will be false. So process 1 enters the critical section. It will complete its execution faster, sets the value of turn to 0, enters the non-critical section. So both the process 1 and 0 are in the non-critical section. Now again process 0 wants to enter the critical section. So what process 0 will do? It will check the value of turn. Turn is currently 0. So 0 not equal to 0 is correct. 0 not equal to 0 is false. Process 0 again enters in the critical section. Where is P1? P1 is still in the non-critical section. So P0 has entered the critical section second time. So when P0 has entered the critical section for the second time, P1 is in the non-critical section. So P0 will finish executing in the critical section, sets the value of turn equals to 1. Second time P0 comes back in the non-critical section. Where is P1? P1 is still in the non-critical section. Now what's happening? Value of turn is 1. P0 is in the non-critical section for the second time. P1 is in the non-critical section for the first time only, but it is taking more time in the non-critical section. So what happens? If P0 wants to enter in the critical section for the third time, it cannot because turn is equal to 1. So 1 not equal to 0 will be true and process 0 will be in the busy waiting condition. So what's happening here? Process 1 is in the non-critical section and it is blocking, being in the non-critical section, it is blocking P0 to enter the critical section. So the fourth condition is not satisfied. What is the fourth condition? It says that when one process is in the non-critical section, it should not block the other process to enter the critical section. So this algorithm fails. It doesn't satisfy the fourth condition. That's why this algorithm also is not a good solution for mutual exclusion. Are you able to hear me? Can you hear me, please? Okay. Are you able to understand? Okay. So strict alternation algorithm also fails. It fails in the fourth condition. So what we need to do? Somebody has asked me, sir, it is similar to deadlock. The fourth condition, sorry. Sorry. Strict alternation algorithm will not satisfy the third condition. Strict alternation algorithm will not satisfy the third condition. One question is asked by Vamshi, is it similar to deadlock? See, fourth condition of mutual exclusion is something related to deadlocks. Pujita has asked a question, is critical section preemptive or non-preemptive? See, critical section is block of code. So critical section is not any special thing. It's a block of code. And the block will contain the code to use a file or shared memory. So you cannot say it's preemptive or non-preemptive. It's illogical. Whenever any process is executing a block of code, see, whenever a process is executing an instruction, an interrupt occurs, the CPU will allow the process to complete the execution of instruction. But after that, it has to be preempted. So preemption can occur to any process at any point of time. Only thing you need to understand is that the CPU will allow to execute the entire instruction. Only after that it will preempt the process. It will not preempt a process in between the execution of the instruction. So if you have an instruction like A is equal to B plus C, so while this instruction is getting executed, if an interrupt occurs, the CPU will not preempt the process in between. It will allow the process to complete the addition operation. That is, it will allow to add B plus C, then only the process will be preempted. So processes can be preempted at any point of time. Whether it's executing the critical section or non-critical section, the process can be preempted at any point of time. So what we need to do here is we need to design a solution in such a manner that if at any point of time the process is preempted, it should not lead to error in the shared resource. Right? That's what is the meaning of it. Okay. So let us move on to the next algorithm. I'll finish the class after this algorithm because I have an online meeting with the HODs and the chairman. So this was the strict alternation algorithm. Next, we'll move on to second algorithm. The previous algorithm I had named as mutex 1. This I am naming as mutex 2. Mutex 2 means mutual exclusion 2. So this algorithm is mutual exclusion 2. The first algorithm was mutex 1. In mutex 1 was satisfying first condition, second condition. It was not satisfying the third condition. It was satisfying the fourth condition. But the good solution should satisfy all the four conditions. Let us see next algorithm whether it satisfies all the four conditions. Now see, there are two processes here, process 1 and process 2. Both are sharing a common resource, file X. Both can execute at any number of times. That's why the condition is always true here. P1 can execute any number of time, P2 can execute any number of time. The condition will remain true always here. But the condition is to be checked only when process 1 wants to enter the critical section, or condition should be checked only when process 2 wants to enter the critical section. See, what was happening in the previous algorithm was that if one process is taking longer time in non-critical section, it is stopping the other process to enter into the critical section. That was the basic problem in the algorithm. And that's why it was not satisfying the third condition. That is, a process should not prevent the other process to enter the critical section when it itself is in the non-critical section. Now here what we are doing is we are using two flags now. There are two flags. One is P1 using flag, it's Boolean. Boolean means P1 using can take a value true or false. There is another flag called P2 using flag. This also is Boolean. Now, if P1 using is equal to true means process 1 wants to enter the critical section. If P2 using is true means P2 wants to enter the critical section. So I repeat once again, there are two processes P1 and P2. So if P1 wants to enter the critical section, it should set its flag to true. That is, P1 using should be set to true. If P2 wants to enter the critical section, it has a flag associated with it. It's called P2 using. So before entering the critical section, P2 using should set the flag to true. At the beginning, P1 and P2 using will be false. So P1 using is false. P2 using will be false, which means to say that neither P1 is interested to enter the critical section, nor P2 is interested to enter the critical section. So P1 using is false, P2 using is false means process 1 is not interested to enter the critical section, process 2 also is not interested to enter the critical section. That's the meaning of P1 using false and P2 using false. Both the flags are false. No one is in the critical section. Say in the beginning, P1 wants to enter the critical section. So what P1 should do, before entering the critical section here, it should check what is the position of P2. So it's checking, is P2 using true or false? P2 using is false. So while loop has a false condition here. So while loop will not be executed. Once also, the control goes to the next line. Next line, what P1 using will tell that I am interested to enter the critical section. That's why I'm setting my flag to true. So P1 will set its flag to true. P1 using equals to true means P1 is interested to enter the critical section. So after setting the value of its flag to true, it will then enter the critical section. So P1 is in the critical section. As I said earlier, that a process can be preempted at any point of time. Each process is given a time slice. After the time slice is over, the process will be preempted. So P1 will be preempted after some amount of time. And here it gets preempted when it's in the critical section. CPU is given to process 2. So what process 2 will do? It will check whether P1 using is true or false first. So what is P1 using? P1 using is true because P1 is in the critical section here. So P1 using is true, which means process 1 is interested in the critical section. So if this condition is true, since the while loop is terminated by a null statement here, as long as the condition is true, process 2 will be continuously testing the flag P1 using is true or false. So it will enter into busy waiting. It will not be allowed to enter the critical section. So when process 1 is in the critical section, process 2 will be outside the critical section. After process 1 is given the CPU back, process 1 will complete the critical section. Then it will set the value of P1 using to false. So this becomes false now. P1 using becomes false. Once P1 using becomes false, this condition will be false. So this condition is false means while loop will not be executed. It will go to the next statement, sets the value of P2 using to true. That means process 2 is interested to enter the critical section. So process 2 will enter the critical section. Process 2 will enter the critical section. At that time, process 1 will be in the non-critical section. So the condition is satisfied. That is, when process 1 was in the non-critical section, process 2 was executing the while loop. And when process 2 is in the critical section, process 1 is in the non-critical section. So the flag value of P1 using is false, P2 using is true. After the non-critical section, if process 1 wants to enter the critical section, it will check the value of P2 using. P2 using is true. So process 1 will be in the busy waiting state. It cannot enter the critical section. So what we see is that in mutual exclusion 2 algorithm, when process 1 is in the critical section, at that time process 2 was checking the P1 using flag. And when process 2 is in the critical section, process 1 will be in the non-critical section, or process 1 will be stopped here only as long as P2 using is true. So we see that the algorithm is successful in implementing mutual exclusion, but there's a problem here. Let us see where it fails. Now see what happens here. Initially, P1 using is false. So P1 using is false initially, P2 using is false. Both the processes are not interested in the critical section. Process 1 wants to enter the critical section. It will check P2 using. What is P2 using? False. After checking the flag here, and before it goes to the next statement, it will be preempted here itself. Means what's happening? Process 1 has executed P2 using here. Process 1 has executed P2 using here. It has found that P2 using is false. But before it could set the P1 using flag to true, it gets preempted. Where it gets preempted? It gets preempted over here. That is, after checking the flag and before setting the value of flag to true. Now what happens? The CPU is given to process 2. So process 2 is given the CPU. What process 2 will do? It will check the value of P1 using. What is the value of P1 using? It's false. So value of P1 using is false. Value of P1 using is false means it will set its flag to true. So what happens? P2 using is set to true. This becomes true. And P2 will enter the critical section. Right now P2 is in the critical section. Value of P1 using is false. Value of P2 using is true. When P2 is in the critical section, it gets preempted. CPU is given to process 1. Process 1 has already executed while statement. That is, P2 using was false at that time. When the first time P1 executed, at that time the value of P2 using was false. It will not execute the same statement once again. So when it gets the CPU for the second time, it will not execute the same statement once again. It will execute the next statement. What is the next statement? It will set its own flag to true. After that, process 1 also enters the critical section. So what is happening here? Process 2 is already in the critical section over here. Now process 1 also enters the critical section. So both are in the critical section at the same time. So this will be leading to what? When both are in the critical section at the same time. Failing of which condition? The algorithm has failed. Both have entered the critical section at the same time. First algorithm was failing in which condition? Third condition. the process being outside the critical section, sorry, which can fourth or third? Just go back.
First.
See, this algorithm fails in the first condition. Both are entering the critical section at the same time. If you go to the previous algorithm, mutex 1, strict alternation. When P1 is in the non-critical section, it's just blocking P0 to enter the critical section. So if you see the conditions over here, process, sorry, mutex 2 doesn't satisfy these two conditions. Both are entering the critical section at the same time. So this condition is not satisfied by mutex 2. So no process running outside its critical section may block any process. This condition is not satisfied by mutex 1, that is strict alternation algorithm. So mutex 1 failed here, mutex 2 failed here. Both the algorithms have failed. Next, we have to find out now whether there is an algorithm that will satisfy all the 4 conditions. So next algorithm here is mutex 3. So we'll see mutex 3 algorithm in the next class. So I want to stop this class here. Can we have the class tomorrow? So Satvika has given a message there. Can we use avoidance in this case? See, deadlock avoidance is different and process synchronization is different. A banker's algorithm and all cannot be implemented here because we are using shared resources here. So we have to implement the solution for mutual exchange using algorithm. There is an algorithm called Peterson solution. We'll come to that algorithm later, in which we can show that all the 4 conditions are satisfied, right? So can we have the class tomorrow at the same time? So are you comfortable with this online class? Anybody who wants to speak, you can unmute their microphones and can speak. So Nilima has asked a question: if the preemption was not done at the time that we assumed, then the algorithm will work. Yes, the algorithm will work if there is no preemption. And Pujita has again asked the question: why don't we assume process 1 equal to true before while is checking process 2 is true? I did not understand the question now. This condition what you have mentioned is checked in the mutex 3 algorithm. There is third algorithm. I'll discuss that. Pujita, I'll discuss this in the next class. I find that there were 106 participants and suddenly I see only 88. Any particular reason for that? why those people have left. Okay, what time shall we have the session tomorrow? Vishalakshi, madam, can you listen to me?
Yes, sir. Tell me, sir.
So tomorrow shall we have the class at the same time?
Okay, sir.
What I want you to do is you please talk to the students.
Okay, sir.
Students can call me on my number and ask me doubts. And if they have any kind of issues, please let me know whether they have found any difficulty in today's class. Anything is to be, uh, streamlined. Please let me know so that we can go in the next class. But see that the strength increases because it's an important topic. It's not so easy to understand.
Yes, sir.
It's little bit. This is the most logical part of operating systems. The algorithms are a little bit difficult when you go next algorithms like Bakery's algorithm is there. You have sleep and wake up algorithm, semaphores, and you have this monitors. So things will get difficult there. So if you have any algorithm to be repeated by me, please let me know. I'll start with the repetition tomorrow and then we'll go for the next topics.
Okay, sir. Definitely, sir.
So please send me your feedback on WhatsApp. About today's class. So let us finish this meeting and thank you so much for attending this online class, and I wish you all to stay safe and protected, and I hope that you are staying in home, you are not coming out. Please don't come out, please stay safe, please be protected, and wish you a safe life. So let us meet tomorrow. Thank you so much.